Okay, thanks. Hopefully everyone can hear me. I'll assume that's the case and maybe even see me. I'm waving wildly. And now for something slightly different, moving to an application area of the fabulous samples from Apollo 17 that we've heard so much about in previous talks, like the one that was just given. A group of us, mostly some expert engineers in non-destructive evaluation and microwave techniques, at Goddard have been evaluating the potential of samples from, in particular from this Apollo 17 grouping, the 71035 very high titanium basalts, as a type of characterization to search the moon for such materials as a potential value for science and also for the resource prospecting applications intrinsic to Artemis and to having our crews on the moon. And in order to do that, we've looked at, and let's just go to the next slide. We've looked at this particular sample that we've been working at for the first time ever in terms of a kind of CT scan like electrical properties mapping. And like many of you are aware, and the Lunar Source Book describes beautifully the bulk electrical properties of lunar samples from all the Apollos, from lunar meteorites, wonderful measurements, bulk samples made for one number describing the sample. And unfortunately, electrical properties don't work that way, as we can see inside the mineralogies of these great samples. So we took it upon ourselves, building on the work of Gary Olhoff, Tommy Gold, and others, to basically look at the intrinsic electrical variability in correlation with mineralogy of some lunar samples, in particular 71035, which I'll get to, and comparing that to how radar remote sensing with the modern techniques could actually allow us to see these things. So let's take a look at the next slide, if you would. So we've focused on two samples that we've been working on for a parallel study of the microcratering history and physics on these samples, because they're zap pitted. One from Apollo 17, 71035, wonderful sample collected at Station 1A, and the other bulk sample at Apollo 14 of an impact melt breccia. We looked at others as well, but these measurements take a while because we're trying to look at the dielectric tensor as a function of angles, the way CT scans do in X-ray. So we're going to focus on those and the implications. Next slide, please. So first, just to remind you, the one sample of great interest to us is this VHT basalt. Many have studied it. It's a fascinating sample with a very interesting potential for high dielectric properties in the wavelength range, in the frequency range that the kind of radars now flying around the moon in Chandrayaan-2 can actually detect. And so as we move into a further generation of these radars from the community that builds these great instruments, the question is, could we detect the signature of these things as it's disseminated in regolith and elsewhere? Next slide. So this is a new class of measurement. So the first thing we did with the samples, and this is kind of the bottom line up front, was to conduct variable scale X-ray computer tomography scans and related scanning electron microscopic scans of the samples. And you can see here 71035 on the left, and this beautiful zap-pitted impact melt breccia from Apollo 14 from Falmaro, 14304 in the middle. And one can see they have forests of high backscatter in X-ray. Many of these are metal oxides and metal sulfur species. We've characterized those, as I'll get to. But on the right, you can see a funny little kind of photograph that shows the wide variability of the electrical properties of these as a function of orientation. A bulk number is not going to do justice to this complexity of the way these kinds of materials, which of course are also intrinsic to the regolith, behave. So let's look at why that's the case. And we've shown that, and I'll show that coming next. Next slide. So one thing we observed in just looking at 71035 is that there are beautifully rendered at the surface blades of the ilmenite that's been described petrographically for this sample nicely. And so we've characterized those. You can see one here in laser confocal microscopy appearing right at the surface and this is at about a 30 nanometer scale imaging on the sample. And we just discovered this as we were looking at damage from micro cratering. Next slide, please. And so we also looked at this in terms of, could we segment and now analyze the actual volume distribution of the electrical conductors in this sample, including, of course, the ilmenite and the other opaque phases. And so next slide, we've done that using a bunch of algorithms. And this shows that in the most conservative estimate, the bulk volume of those metal phases dominated by ilmenite in this forest of these laths in the sample is 16% by volume. That number could be as high as 22% if we allow other phases to contaminate this kind of calculation. And so we think this is a lower estimate. Petrographic estimates have the number up around 12%. This is a very high dielectric material. And in most radars in a lab, in an anechoic chamber, will light up like a firecracker. Not really, but literally. Next slide. And so we developed a technique then that builds on the previously used techniques that are widely in practice in many places, the resonant cavity perturbation method that do bulk measurements of the dielectric tensor, to do these measurements as a function of orientation, using a waveguide, a precision network analyzer, and software to forward model the behavior as a function of angle, to get it really a kind of CT scan-like view of these rocks electrically at the frequencies that radars operate. This just shows the lab setup and an example of an output product showing just in this case, the loss tangents, simple ratio of the real and imaginary parts of this parameter for that particular sample, the Apollo 17 71035. And you can see I have vectors there in colored showing that it's intrinsically anisotropic. Next slide, if you would. And so in order to do this work, we have to measure the sample at multiple orientations in a waveguide, which is a kind of chamber where the reflections of electromagnetic radiation can be measured as a function, as a tensor of S parameters. And then we have to model the shape of the object using a variety of techniques, including laser scanning and X-ray computed tomography. So we've done all that for several lunar samples, some Martians, and some test samples of calibration materials. This just shows 71035. You can see the input materials. Next slide. And this shows the results. So here's a sample that at first examination you'd think is just has a high dielectric constant. Well, it turns out it actually has the greatest variability in its imaginary part of this dielectric tensor, and showing that the loss tangents, the parameter that we can use to estimate how well radar frequency energy would propagate in it, are extremely high. In one case of one orientation, the number is 0.28. Now that's a factor of 3 above the highest numbers reported in the literature for the bulk loss tangents of samples studied previously. So this is just one orientation. We're now working on producing a huge field of these measurements. This is a sample of just 4 kind of orthogonal basis vector ones. And you can see the variability goes up by a factor of 3. Next slide, please. And so if we plot that, you can just see the shape with the vectors showing the magnitude and the little hodograph on the right, showing that in fact, some of the values are even as high as 0.4. So these things are basically like a wall of metal, even though they're only 16 volume percent, that could be seen by a sensitive high radar bandwidth kind of radar system. So these would actually be detectable in the domain of the kind of instruments we build now. Next slide, if you would. And so we also measured this impact melt pressure, partly because it was interesting electrically, partly because we were measuring the microcraters, and we saw a different variability, even greater variability in some of the parameters. In fact, its index of dielectric anisotropic variability is over 2. That means that it's got, a 220% variability just in looking at the basis vectors. That's extraordinary, folks. Normally, we'd have one number characterizing this rock, the dielectric constant's 4. That's typical of the literature. Well, in fact, that's not a good description of how this sample or materials made of this sample as a regolith would behave electrically. And this has been long known. It's just very tricky to make these measurements. Next slide, if you would. So just to plot the variability, here's a hodograph showing the variety of just the loss tangents for the 2 Apollo samples. You can see they're not clustered around the center, but they're all over the place. Many of the values very high. This degree of anisotropic behavior means that the electrical properties, the scattering behavior seen by surface radars, orbiting radars, handheld radars from crew members are going to be all over the place. But it does offer the potential for detecting certain families of them, and not only the water ice, of course, of great interest. Next slide. So we've looked at that in comparison to a classic Martian sample, happens to be the calibration sample in the Sherlock instrument on Mars Perseverance. You can see that at the top that's SAU 008 versus the two lunars. And it turns out that the lunar samples have a much higher dielectric anisotropic behavior than the Martian. The next slide, if you would, please, just shows a summary of that index, which is a simple statistical parameter. And so you can see that the one lunar sample typical of these impact melt breccias commonly found at Apollo 14 and many other Apollo sites, it's literally the largest degree of anisotropic behavior that we've seen. And we've looked at all the standard, many standard terrestrial rocks, blasted basalts from Iceland, from Hunga Tonga that just blew up, from other types, and including ones with pretty high FeO contents. And none of them are like this. So this tells us the moon is giving us an opportunity to use the directional dielectric properties as a tool for discovering where these things are distributed. Of course, we can see them in infrared remote sensing as well, but we can also use their electrical properties to find them. Next slide. And so we've developed radar scattering models using a non-IEM approach, meaning not this kind of standard quick math, but actually simulating all the different perturbations to see how these things would look at the moon if we were looking at them both imaging and near nadir in a way to retrieve how they might be distributed with depth. Next slide just shows the bottom line.
Warning.
Okay, and basically it shows that if you have these kind of high behaviors, you're not going to see anywhere into the lunar surface. They're going to show up as literally a wall of material, like you just bounced a radar off a metal side of a building, and their penetration depth limited to less than the wavelength of the radar. You can see that over in the far left. These are curves of the different behaviors as a function of loss tangent. So typical moon is 0.01 to less. It shows you can see deep into the moon, as we hope to do and are doing. And when you have these kind of Apollo 17 samples, we're not going to see anywhere. Next slide just summarizes that in another thing. And basically for today's radars, that SAR noise equivalent sigma naught capability is the sort of sensitivity level that they could have. And for seeing deep in the moon, we need extremely low loss regolith, nothing like the samples that we've been measuring here from Apollo 17 or even the Apollo 14. So it means that we have an ability now to use radar, next slide, to see, next one, to actually see into the moon and to find the surfaces that are rich in these metal oxide rich materials, which could be resources. And so we have the tools now to make these measurements. They're not easy to make, a lot of computer modeling to get the forward models to work through large forests of parameters. It's kind of a four-dimensional search space, but we think that the numbers are really encouraging from these Apollo rocks, and we want to continue to work these as a tool to use what we learned at Apollo 17, next slide, and apply it forward across the whole moon in the future class of radars that we think could be flown in support of Artemis for resources, but also for a general imaging situational awareness. Some of these radars have potential of seeing things down at sub-meter scale. And so we think that would give a nice connection between the work from the Apollo samples and the future remote sensing that will support our women and men crew on the moon. Final slide, and I'm done, next slide, is to thank everyone at JSC and the curator group with Ryan and Juliana and others for providing the samples, the work of pioneers who helped us get started on this, going back to Gary Olhoff and others literally 30 years ago, and the encouragement of Keith Rainey and others point out what radars can really do using the moon, going way beyond the excitement we've gotten from the mini RF on LRO and other radars like the DFSAR on Chandrayaan. So thanks everyone, really appreciate the time. Back to you.